because there are various things which I would like to present in a rather informal way. The three main topics that I want to explain in the remaining parts of the course is, on the one hand, how this big reservoir of S0 prime allows you to get a more unified view on the Fourier transform. As a colleague in Germany, Jens Fischer, was putting it also in one of his papers, there is just one Fourier transform. It's not the view of engineers. There's a Fourier transform for discrete signals, the Fourier transform for periodic signals, there's a Fourier transform for decaying signals or so, but we will see that they're all fitting together, and this is something that I think can be described better in a more informal way. The second thing will be more about Gabor analysis, so why these function spaces are good for Gabor analysis. Actually, Gabor things arising in Gabor analysis and LP spaces don't fit extremely well. L2 is perfect, but L2 is usually in every function family, so to say something works good for L2 doesn't tell you which family would be appropriate. And the third thing is, as indicated already, the kernel theorem, which is a way to represent linear operators by abstract generalized functions of two variables, and which is exactly the analog of a matrix representation. So you can say what happens if a matrix is commuting with translation, what happens if it's a multiplication operator. You would say, well, it must be supported, the distribution must be supported on the diagonal. And then, of course, it's nice to say, well, but it's actually a diagonal on a distribution living on the diagonal. So it's a difference. When you have functions, you can also say a function is a function of two variables. It only takes non-zero values on the main diagonal of a matrix. Or you can say, I just have a diagonal. But one is zero elsewhere and the other is not even defined elsewhere. Okay, so just to remind you, the general setting is we have a zero, and as a subspace of L2, we have seen it's continuously embedded, and we can view all this as a subspace of S0 prime. And we note that we have on S0 prime, we have both a norm topology, so we take the 0 prime, and we have a weak star convergence. So what does it mean that sigma n converges to limit distribution? And I like to call the limit always same symbol with a 0 in bin. And if this is a norm without symbols, this means I have to take the 0 norm, but the 0 norm is can be shown to be equivalent to the maximum of the spectrogram. So S0 is integrability, dual to it is boundedness. We can see that you will have to look at the Vg, or maybe we take a Gauss function, Vg0, and either we say uniform convergence of the spectrograms, or we say spectrograms of the difference. Clearly, taking the spectrogram is a linear procedure, so the most elegant way would be somebody is saying, I have two functions having a bounded spectrogram, the difference will be also a bounded spectrogram, but the difference melts away and goes to 0 as n goes to infinity. And then I'm saying, that's a standard statement that probably you have heard or will hear a couple of times from my side. The audio engineer, these are the people who look at these spectrograms and they inspect if the quality of the recording is good. They sell you a cheap rectangular part of the spectrogram as perfect reconstruction. They say, I have recorded with high quality 3 minutes of a piece of music from 0 to 20 kilohertz. And I would say, this has nothing to do with uniform convergence. It's just local, and local in time and frequency. Well, I agree, it's at the area of interest. You're not interested about the noise in the break before the concert. You're not interested in what a bat might hear at ultra frequencies. You're interested in what you can hear and what you are interested to hear. So somehow to say somebody has only given you a weak star approximation sounds like he's given you very weak information. It sounds weak or so. But I would say he's giving you a finite dimensional thing because that's what you can store. You can store finitely many coefficients. And if he's doing a good job, and Gabor approximation is a reasonable thing, you don't take a full square, but you discretize that more or less down to the dimension that this has. So if you have a certain amount of frequencies, then you can say what is the Shannon-Nyquist rate. So if I would sample the musical signal up at the Shannon-Nyquist rate, I store those coefficients in the form of an FFT. I have about the minimal thing. If you are doing much less, you have no chance. And if you, in addition, then you do what the people designing MP3 is doing, that you use psychoacoustic effects, and you even throw away things which are so small that you cannot hear them. Also, they could be measured. Then you are even better. But that's the main idea. Is norm convergence is very good. We are in a dual space, but we should go for weak star convergence, which is sigma n. I'm writing weak star, or we're writing sigma 0 is the weak star limit. And then we're saying if and only if, when you apply this, we can write it in this way. Sigma 0 of lambda, which is a scalar product of sigma n minus sigma 0, applied to my Gabor atom sitting at position lambda, is going to 0 for every lambda in our time frequency plane. So maybe I'm writing even TFD, which is time space, again with frequency space, but you can think of image processing. That's a 4-dimensional phase space. That's why TF is time frequency space or phase space. So what I'm saying is going away from uniform convergence to pointwise convergence. Now it's a little exercise in functional analysis that if you have convergence for individual elements, then you can have it for finitely elements. So if you think that somebody wants to have really convergence over a rectangle, you would probably make a fine grid. You find an index that at least, 10,000 points, you have an approximation error of epsilon over 3. And then you need an argument that, well, these Gabor atoms are moving only little around, so that the remaining can be only, let's say, twice as big. So this is okay, but this has to be done for all G in S0. And the good thing is, or some non-zero G, I'm writing G0 to indicate it could be the Gauss function, it could be one thing that you know already is in the space, like a triangular function. You can take a classical kernel, you can take a plateau function, or so we know a lot of good functions are in the space. And that's even in that sense a little surprising, and as to be also discussed in the first point. I mean, why can I replace the individual Gauss function by another one? So why is this uniform convergence principle independent of the window that you choose? And the idea is relatively clear once you have this atomic decomposition. So I have probably not explained it in all detail, but the story is the following. You can say, I would like to have my favorite function, maybe let's say trapezoidal function or triangular function, but it has to be in the space. And then I'm saying, then there exists a map for every f in the whole space. So now I'm trying to represent all other functions by sums. There exists a sequence Cn and a sequence lambda n. The sequence of coefficients is complex valued and absolutely summable, so you sum from 1 to infinity, and that you can reconstruct the f from these coefficients, sum n g, I'm writing the one upstairs now, lambda. And that's now over some lattice or even more general. You can have different versions. When I met the engineers the first time, I did not know anything about Gabor analysis, and I explained to my colleague Franz Lavac that I have a space which I think could be useful, and I can say, if you give me an f, I would need a sequence of lambda n. Yeah, you can also, the better way would be Cn g lambda n from 1 to infinity. So the old description was, if you give me an n, I would individually for every f fabricate a function. I would choose points in the time frequency plane, and somehow the idea was I would write a continuous reconstruction formula, make a Riemannian sum, and there's a remainder. And then I take the rest and then make a finer Riemannian sum and a finer Riemannian sum. I have to only control that actually this sum can be controlled by the S0 norm of what I represent. So that is an important fact that I should have mentioned before. So if you tell me how big your function is in the space, I would have a representation with approximately that cost. and so that the infimum over all these possible representation would be an equivalent normal. And I thought it's very natural that you need all the building blocks, because if you just stay with the Riemann sum, you have an error. And he was saying, well, but isn't there a statement of Gabor that you don't need all the lattice points, that you need only the ones in the integer lattice? And also, how do you compute the coefficients? And I said, I use functional analysis. I know my spaces that you know already is the smallest one. So if I write the space with atomic decomposition, I have only to prove it's inside the space, but no, and it's invariant, obviously, so it cannot be smaller than the smallest. So implicit, there must be a representation. I don't have a recipe. Nowadays, of course, I would say, I take a Gabor representation, you give me a Gauss function, then I take any lattice with a times b less than 1, and I would say the coefficients are just that the first version would work. I would take the dual of this one. I know it's again in a zero function, or even a Schwarz function. I would compute the coefficients as the samples of a short-term Fourier transform sampled at the lattice. It can be everything slightly better than Gabor. So Gabor was only wrong with the idea that he could do it at the critical density. But this is not so important. Now, you can imagine, for example, if you say I have now a second Gabor window G2, then I could choose my F to be that second Gabor window. So I have to understand what happens if I don't choose my G0, let's say, but a finite linear combination of G0. And then it's clear, well, if you control the L1 norm of a short-term Fourier transform and then you shift the window, that means an offset of the function. That's same L1 norm. If you have a linear combination with such coefficients, you control it. If you take the limit, it's just absolutely convergent. L1 is over time frequency space, is a Banach space, so there will be no problem. And you can say, I can control the a zero norm or the sup norm or all this. If I can it for one, I can do it for another. But this is symmetric, so it's two windows are equivalent. And that's why uniform convergence is fine. Now, again, the other one is if you have it pointwise, you go for uniform convergence over compact sets, and I think that's the best way of doing it. Now, so we have seen that in this spirit, this S0 prime space, the test functions are dense, and recall that S0 is weak star dense in S0 prime. And you could say I could do this also via Wilson basis. That was one Wilson basis. That would mean I have an isomorphism between the Banach-Gelfand triple S0, L2, and so to L1, L2, and L infinity. That would be an isomorphism of Banach-Gelfand triples between, let's say, I should write it S0, L2, and S0 prime. So everything I'm doing in my Banach-Gelfand triple, I could do in sequence space level. So the only thing is, what is weak star convergence in L infinity? It's just coordinate-wise convergence. So clear enough, every sequence which is bounded can be approximated by finite sequences, finite and then zeros, in the sense of pointwise coordinate-wise convergence. You just take more and more, and the index set maybe is a subset of all finite coordinates index sets. Okay, you have this, or we had another way which I think is more useful for practical applications. You don't need Wilson basis. You can say if you take a distribution and you smooth it, you get already a continuous function, and then you can multiply it, and for some non-trivial reason you are getting into S0. So if you are convolving your sigma, let's say E alpha, or maybe even more concrete, I take ST rho G0, I take a Gauss function. I think it's delta 0, but I write in this way with my sigma. Then this is supposed to be a continuous function. And then I stretch the Gauss function or anything which has value 1 and is smooth in the 0. And this will go in the weak star sense. It will go in the weak star sense to just sigma. And you can say, we can even do the proof in 3 lines, I hope. So if you apply this here, apply it to F. Then you just, we will learn how to use the rules. We have sigma, smooth version of sigma in the bracket. So what we have to do is to say when we multiply with the dilated Gauss function, So I'm writing, just copy st row of G0 with S. That's a distribution, certainly. But now I multiply the action with d row G0 times F. And then I'm saying, well, but this is something I cannot still do. I want to have sigma of something. And then you have to say, well, if you are convolving a distribution, you again view it as a joint operator. If it was everything were functions, you would put it on the other side. You would flip the function, but the G0 is already symmetric. Stretched version of G0 is symmetric. So maybe I write it and erase it afterwards. It's, it's 0 applied to st row G0, the whole thing flipped. But then we can remove it. Convolved with inner term is d row G0 times F. And that, of course, goes to sigma F. And you just have to say, well, I'm changing two things. First, I apply one operator near the identity, then another one. And you can easily prove by going with a term in the middle, maybe you leave out one of the operators, that it's going to this in the norm because dilated Gauss functions in the zero norm are good. Remember, our functions are absolutely convergent of pieces. So if it's good for finitely many, it will be good for every f in S0. And then you apply this st row. If you have gained a lot, it preserves the small error that you have, but it makes the smoothness part better. So in this way, you have seen for whenever you apply this nicely modified thing, you get weak star convergence. But why are we ending up in S0? So somehow I only told you it's true, and it's like the Schwartz space. The Schwartz space allows the same thing. A Schwartz function convolved with S0 prime, a Schwartz function convolved with a temper distribution, you could check. Well, you're smoothing it. So you're getting a temper distribution which is smooth. Actually, you get a function which has all the possible derivatives, but each individual derivative grows at most like some polynomial. So you might get something like third derivative is like x squared. But when you apply it to a test function, it will be okay, so in that sense. So if you multiply afterwards, you get back to the Schwartz space. It's completely different here. Here I have to do it again, try to do it in one line. What was S0 in the amalgam terminology? That's one of the situations where these amalgams and their convolution relations are really handy. I have to convolve it with the dual. And now you may guess, what is the dual of a space called FL1L1? Well, it's FL1 dual. Remember the story with the pseudo measures. And absolutely convergent Fourier series, you have L infinity in terms of Fourier coefficients, or you call it pseudo measures. But for me, it's just, if you start with temper distributions, it's the space of Fourier images of temper distributions. If you have not defined it, you can define it, or you say it's the dual space of some nice algebra that you call the Fourier algebra. And then the dual space of L1, finite sequences are dense, test functions are dense in FL1, so this is justified. And then this is a bracket, and then I'm multiplying again with S0. Maybe I do it like this. Because now I use the convolution theorem. I'm saying inside the bracket, I will get a result with a amalgam space. Now the question is, what is FL1 convolved with FL1? And the harmless thing, as usual, if I have f's, then I go to the other side and f will disappear. So I apply f to the -1. I'm asking you, what happens if I convolve L1 with L infinity? Back to kind of normal argument. L1 function convolved with a bounded function, you pull out the maximum of the function is certainly FL infinity. No, sorry, F. No, yeah. No, I'm doing a stupid thing now. I should repeat my explanation. We're asking about the convolution of FL1 with FL infinity. Therefore, we should go to pointwise product of an L infinity function with an L1 function. And I was on the wrong track. So if you multiply an L1 function, and now this is the guy on which you operate by multiplying with the bounded function, you're getting L1. Read backwards is FL1. The next thing, if you convolve an absolutely summable function, so you're doing convolution on the integers, then of course you're only getting L infinity. So somehow the idea is, when you have a continuous case, then the good quality FL1 is imposed on the convolution product. If you have something discrete, there is no smoothness aspect. You cannot improve the decay rate. L infinity is not decaying, so we hope to preserve the boundedness, and that's of course trivial. And now we multiply with S0. Now I write it as FL1 with L1. But again, the argument is coordinate-wise. I will get into an amalgam space by looking at the question, what is going on with FL1 times FL1? Well, it's called the Fourier algebra, and the convolution theorem says L1 convolved with L1 is L1. Therefore, pointwise, this must be FL1. So we have an algebra, and all the norm estimates are, of course, okay. But now we improve the quality. The function was only bounded L infinity, but it was not going to 0. But now we multiply with a sequence decaying, and then clearly this is L1, and this is therefore S0. So this was the argument why we have this product convolution operator. So an operator of the form sigma goes to, usually I like to write the elements which are multipliers H. H times S with G. I call this, and I usually read it in this way, a product convolution operator, because I'm applying the product first and then the convolution. Or you can say I'm doing a convolution first, which is a smooth out. That was our discussion case. Multiply afterwards is a CP, a convolution product operator. Same type of argument by analogy. Our mapping map from S0 prime to S0. And I think you can make an exercise. If somebody says that the sequence sigma n is weak star convergent to sigma 0, then applying these operators T, let's say T1 and T2, T1 and T2 map to norm convergence. So we have T 1 or 2 of sigma n minus T of sigma 0. Each of them is in S0, but they're actually norm convergent. So you see, we have not lost too much information by going to the weak star convergence. Now I'm going to the next thing, which is how can we go from abstract harmonic analysis to more application-oriented harmonic analysis, which for me, I'm trying to promote a concept for some time now, which I call conceptual harmonic analysis. And it's the idea that abstract harmonic analysis tells us we have different scenarios, but they are they go by analogy. First we do one case, maybe Fourier series is the classical approach, and then we stretch, we do some vague transition, and then we say probably in the continuous case the forward and inverse Fourier transform look like this. If we are mathematicians, we are saying this is heuristic, we want to prove it, and we have seen how the proofs go. How can we justify the integration? We'll use Lebesgue integral. That's kind of established theory already for the last 50 years. And then somehow FFT came in. When we do the computer, you use the FFT. Engineers write papers saying this is the model, but now we go to the computer, we do FFT, but rarely they discuss really the transition. And so it's good to have all these Fourier transforms in one case. So I will try to demonstrate it in a rather drastic way with my objects here. The first thing is what you learn, and I have already mentioned it in the course earlier, that we're learning that a function which is periodic is a function on the torus. So function on the torus, I look from above. Here I have the unit circle. I think for me now the 1 is here, and you parameterize it by walking around. Well, clearly an ant which is living in the torus world, she would go around and she would say it's infinite or so. But somehow we have learned that we should map everything on the right group to do the right Fourier transform. But I tried to mark it. I will see if it works. But essentially, what I really think, instead of painting the wall or so, is we have this object. I mean, just wrap it up. If you see this object, you can say, I know what the basic period is. But you can also say, I want to wrap it up. I mean, I want to put it into my computer. So the sampled version of this would be put in the computer. And then, of course, the sampled version could be that I'm saying, well, where do I start my parameterization. Of course, I started at omega to the power 0 and I go to the highest possible power. So this is what you get when you take a discretized version in MATLAB. So you see this, and of course you would like to see more this. So that's why I have these different plotting routines. For the plotting, this is the right data structure. For the interpretation, I have polynomials. I evaluate them at the unit roots of order n. So this trick going to the fundamental matrix, this group theoretical aspect is much more important. So the question is now, how do I get this infinite periodic function from the function on the torus? And I mean, what I do is, of course, I can say, well, I'm taking the function, I'm taking the copy, taking the next copy, go to the other direction. In 2D, I make a periodization. We could say we convolve with the Dirac comb, which has the right distance or so. Now we're in a situation which is nice. I think the Gauss function is nice. It's a Schwarz function. It's in a 0. And we are talking about fabricating something which is in a 0 prime, because it's a bounded continuous function. But it's also somehow the idea that this Dirac comb, the infinite Dirac comb, is the weak star limit of all the others. So we have to not to write the infinite thing, but we approximate it. And we can see what is the effect of all these things when you approximate. So in the weak star sense, this infinite periodic thing is the limit of periodic things. And then you can go to the Fourier transform side and say, well, what is in the partial sum? You take more and more terms. What is going on here? And then we look at the Fourier transform of a sum of Diracs. We know that these are trigonometric polynomials. This is a delta, it's another delta. Each of them gives an e to the I term. And suddenly we are coming to the representation. Well, you see how I mean, now I'm going on the. I'm suddenly changing to the Fourier domain. I'm watching what happens if you put more and more copies of this on the Fourier domain, and you would see how these oscillating terms kind of disappear, except when you are at the sampling points which fit my lattice constants. Let's assume again, this was unit period, and you would say. There's an effect. It goes to the Dirac. There's more and more mass building up. And of course, I mean, we know from the abstract theory, from Poisson formula, the Fourier transform of the Dirac comb will be the Dirac comb. So only the way how the Dirac comb appears is quite different. On the time side, I've taken more and more Diracs. On the frequency side, I have trigonometric polynomials. None of them is decaying. But they are oscillating, and when you apply it to a test function, so you look locally, then you pick out the sampling values and you get exactly the discrete Fourier transform. So that's what we also can do, and what we explained is when you take a function and you periodize it, you get a periodic function. Now we're doing mathematics and theory, so to say, but it's completely consistent with the distributional setting. This periodic function, we're saying you have to wrap it up and then you do Fourier expansion in the different Fourier transform. I'm saying, no, you have really a periodic distribution and it has a Fourier transform which is the Fourier transform of my function. Maybe I'm trying to write it in 2 lines or so. So what is the periodic version of my f that I have shown you on my roll? It's I take my f and I convolve with the SHA. In the distributional setting, it's well defined. It's in a 0, actually it's a bounded continuous function or so. What happens on the Fourier transform side, and I don't do, I mean we could even look at this in MATLAB, what happens as it evolves or so, but if I just take the limit, it must be the Fourier transform of a product. Is the Fourier transform of f hat well defined? Yes, this is in S0. Can I multiply the Fourier transform of the SHA distribution with S0? Yes. Do I know what the Fourier transform of this is? Yes, SHA, Fourier transform is SHA. And if you say I would like to have a lattice Dirac comb at distance alpha, then I would expect that you remember that this dilation operator has to be used. So you would just have a different lattice with the inverse lattice constant, but with some amplitudes, which we also should consider. But first I do this here. And then you're saying, what is multiplying with a Dirac? Well, it's like multiplying with individual. You're getting f of n, no, f hat of n. You get delta n, and you're doing the summation over the full frequency. So in the distributional setting, you are not saying, I make out view a periodic function as a function on the torus, then I do Fourier series expansion and I get a list of values. I'm saying no, I'm sampling the short-term Fourier transform. Of course, the Fourier coefficients of the periodic functions are this. This is f periodic hat in that sense, in the classical sense at n. This is the same as the restriction of the continuous Fourier transform at n. And then, of course, you can say, can I do this more general? And then you can say, well, L2, why not? L2 functions may decay not well enough. The periodization may not be meaningful. While it's in accordance, it would not be meaningful to try to sample an arbitrary L2 function. Maybe you can take a function f in W, L2, L1. That is not all of L2, but locally it's like L2. Then you can still do it. Then f convolved with SHA is in W, L2, L1 convolved with W. Now I'm generous and just say locally it's a bounded measure. Dirac comment boundedly it's L infinity. So this is definitely a function. Well, essentially it's in L2 everything is absolutely convergent. So it's locally L2, globally L infinity. But there is a Hausdorff-Young version which says f hat, this is not a proof now, that's just my argument. It's in W, local properties give global properties, actually a little bit better than I said last time. It's FL1 and L2. But therefore it's W C0 or C continuous time L2. Yeah, so in this case I can say, what can I say about the Fourier coefficients? Well, these are samples of a function which has, if I square it, it has an upper Riemann integral. So this is an L2 sequence. So it's meaningful to not for all of L2 because nasty L2 functions have nasty Fourier transform and sampling on a set of measures here is not okay. Local is a global problem on the time side and there's a local problem on the Fourier transform side. I'm afraid, okay, it's working. Okay, so in that sense, amalgam space appear quite often. And since we have played around so much with amalgam spaces, and I can do it in 2 lines or so, I would like to tell you how I prove the Sobolev embedding theorem for the RD case. So we are on RD. And the Sobolev embedding says that f hat of a function, so function f is in a Sobolev space. I'm thinking I would like to tell you what it means a function is 3.5 times differentiable. Of course, it means somehow 3 times differentiable and the rest is Lipschitz continuous of some order. But in Fourier analysis, we express it that I'm saying if you take the function in L2, the Fourier transform in L2, we can even multiply it with the weight s, and the weight s is the typical weight that you use for such spaces is you take maybe omega to the power 2 to the s over 2. Yeah, so it's sometimes people call it Japanese bracket of omega to the power s. So it's roughly speaking, you can say it's absolute value of omega to the power s. And if you would take power 2, it would be a Laplace operator, so to say. Fourier transform of a 2 times differentiable operator. And you're still in L2, that's so to say the message. And you do it in a smooth way. Maybe I should try to correct this here. Yeah. So it should be omega absolute value squared. It's just a smooth version. You have no problem at the corner. Now, what it means actually is that the Fourier transform is an element of a weighted L2 space. And I told you put the weight in the global component, so it's L2 and it's L2 with that weight. I just write S maybe. So meaning polynomial weight of order S. Now, because I have theorems that can be used, it's more or less reporting how I can play with the amalgam spaces, and the proofs are not too complicated, but it's more important to show you how to use them. For me, it's good that I can write also FL2, because Plancherel tells me L2 and FL2 is the same. FL2 is a little bit better. So roughly speaking, I can say I can apply on this interchange the order by the Fourier transform. But now the thing is, if S is larger than D over 2, then L2 with S is inside L1. This is a very simple argument of the following type. If you say I have a sequence X and this sequence multiplied with this is an L2 function, that's the type of condition I have. The Fourier transform or the sequence, whatever, is in the sequence space. And then I can say, well, but what happens if I want to take away the weight? And hopefully the weight is strong enough that this guy is also in L2. Then I can say, oh yes, X is artificially written as a weighted version of X multiplied with the inverse of the weight, a product of two L2 functions which be in L1. So this happens exactly if you have this condition. So this is the condition that helps me to say now I am inside, yeah, actually I can leave out the F, inside L2, L1, and therefore going back with the inverse Fourier transform, I have HS is inside W C0 L2. So I've shown that this is clearly, I mean, a continuous function where the maxima are decaying because even square integrable, this is clearly C0. Something where even the maxima function are in L2, so it's also in L2. And that's actually another recommendation I can give you. If you see results like if something is decaying in a certain way, so essentially such that the usual Weierstrass test with the upper Riemann sum tells you the decay is strong enough to get summability, very often you can replace it by the Wien algebra. And if somebody is saying, we have something going on very nicely and it's L2 convergent like Shannon's sampling theorem, but it's also convergent in the uniform sense, then you can make a short test and that would say 80% of the cases you can prove in this sense. Now, what is clearly, this is a very big difference. Knowing only continuity, meaning local properties without global control, or L2 globally, having only, I mean, if you have L2, you have L2 locally, no control about samples. So that means, for example, as we have seen before, if you sample a function from such a Sobolev space, one sample per unit interval or so, from n to n plus 1, it will be summable, because clear enough, every sample is not bigger than the maximum over the interval. If you tell me, can I make the same statement about continuous L2 functions, I think everybody of you can fabricate nice examples where, well, it's continuous, so samplings make sense. But you put tiny triangular functions, the energy norm is small because the basis is small, the sampling values are big. So maybe you take triangular function where the L2 norm is 1 over n squared because the basis is narrow, but the sampling values are 1, 1, 1, 1. No chance for summability. So only the combination of smoothness and these amalgam spaces allows you to do this. Okay, so the next thing is just vaguely, and it's really also the vague topology in the background, but now in an informal sense, vaguely to describe things that you usually learn in classical books, and it's not used as a mathematical argument, but within distributions you can make it mathematical. So for example, we have already seen a periodization is like this, the function convolved with a partial sum of deltas, but the deltas go now from minus k as the end up to plus k. So you take more and more, and this is a way to produce the periodic version or so. But what is the other version? I mean, how can we get from Fourier series to the Fourier transform? So Fourier transform. So assume the typical situation is, well, we have such a function, but now we are not happy of having a discrete sequence of Fourier coefficients. So a priori we have a given function. But now we say we would like to view it as a function on the real line. It has a Fourier transform. We have not learned about the Fourier transform integration theory. We know only what we can do with Fourier series. So we would say we take, this. So this is my f again, another f, maybe f1. f1 convolved with SHA-10. Then I could still do a plot or so. Or maybe it's better to have f1 convolved with SHA-1000, and so on, and so on. So we just say, we make the period bigger and bigger. At the end, the period is infinity. The main point that we have to observe is if you look at the Fourier transform side, this lives on the lattice 1 over 10 times the integer lattice. This is living at 1 over 1000. No, that's not my... I have changed the display. Yeah, 1000 times set. So things are getting more and more narrow. And then you would say somehow this goes to the real line, but when you look up engineering books, very often they do it. And now there's actually a problem, because if you would say these are discrete measures now, and you just take the Fourier coefficients, then you would say we are talking about more and more mass in the unit interval. So you should put in the stem command in MATLAB, I would normalize everything. I would tell you, well, we have discrete measures, and if you take the cumulative sum, you have finer and finer approximation. So kind of in a distributional sense, it's quite good. But if they say it's discrete measures because we just compute Fourier coefficients, and then they plot them so that the graph is filled, it's a kind of not so good thing. What you would say is, we are doing now f1 convolved with st rho of SHA, and now rho goes to infinity. This is well defined. This is a uniformly bounded family of measures, because actually somehow the concentration is even shrinking or so. But where is it going in the weak star sense? I think I've shown you what happens. The deltas are moving away. Every person watching a finite interval doesn't see anything more than delta 0 at the end. So it's f1 maybe convolved with delta 0, which is f1. It actually goes to f1. Therefore, we have to look what happens on the Fourier transform side. So on the Fourier transform side, we say this function has a Fourier transform. And we know already everything, but assume we would know only this, pointwise multiplied with the d rho of the SHA. Then you suddenly see these are just Riemannian sums. That would go into f1 hat times 1, and you would say that's the multiplicative unit, and it's f1. But everything happens in S0 prime. Of course, you can do the same thing with Schwarz. Then, actually, that's another small side remark. We can do weak star convergence. I mean, apply in the Schwarz sense or apply in our sense. Is there a difference? First, you can say, well, if I only test against Schwarz functions, they are smaller. It's maybe a weaker statement. Now, in this case, for example, it would be okay. If you only know everything works for Schwarz function, you could use the density of the Schwarz space in S0 to get it for everything. If you think outside of this space, then maybe you can still have Schwarz convergence. That would be really a weaker convergence. And just take Poisson's formula to say it means that, so maybe a small hint about slight difference. It's really not so marginal. If I say SHA hat equals SHA in the sense of S prime, or I'm saying SHA hat equals SHA in the sense of S0 prime. Then there are two comments where I would say it's a slightly weaker from my point of view to have the Schwarz statement. The first one is, if somebody starts with a given object like the Dirac comb and tells you I am in a space, then the information to be in a smaller space, this is really much smaller than the tempered distribution, then it's less. But here it says that if I apply it, and what does it mean to apply the Fourier transform to a distribution? It means I have to apply the summation comb on the Dirac on the Fourier transform of a function, so over the integer lattice, and on the right hand side it would say I have to apply it to the function itself. I take separate summation. So this is true for all f in the Schwarz space, and here it's true for all f in S0. and f0 is much more than the Schwartz space. So if somebody tells you, I've heard the Poisson formula is dangerous, it may be even fail if you are not making any assumptions, then it's quite good to know there is some decent space that I can use for many other things and where you have this property. So you can do these transitions in all these cases. And I think the last thing that is really important is, the question that I will try to answer is, can we use the FFT to compute f hat? So starting point could be, you are giving me information that you have a function in the Schwartz space. Well, actually, I can argue with S0. So we have to have S0. We know already that f hat is in S0. So you expect that if you do a good approximation somehow, that you have chances to work with the samples. Now, it's very important to understand that you cannot expect that taking a Fourier transform of the samples that you would get the samples of the Fourier transform. However, what we can do is we can say we could try to get into the discrete situation. So maybe I'm saying now we're having, maybe I'm doing K. So yeah, I should write. SHA with K is for me the stretched version, with K of K of the SHA, or if you write the sum of deltas, but at, that's not good, alpha. So alpha is delta at alpha times K. K should be the running index here. So we have a Dirac comb with lattice constant alpha. So if I do this and then I apply it to the beta times f, then we can imagine what we get on the Fourier transform side. But first I would like to say we're discussing the combined effect of periodization with sampling. And as we will see, it's important that we make sure that sampling and periodization are compatible with each other. So that's why I was writing the K, but maybe you choose this to be an integer and beta in the set of inverse integers. I'm writing sloppy 1 over n. To have more symmetry, you could say, what if we choose alpha equal 12 and beta equals 1 over 12? That means I have a very nice function, but maybe it could be the Gauss function. My usual claim is it's numerically already 0 from -3 to +3. So if I say I periodize with lattice constant 12, they are very nicely separated. So it should be enough to say I have all the information. So what we can observe in this case here, under this extra condition, so that alpha is a multiple times the beta. Beta is small, alpha is large. You can also take sampling at square root of n and periodizing with square root of n, sampling with 1 over square root of n, periodizing with square root of n. If you are in a continuous domain, you could do it or so, but I take simple integer numbers or so. In this case, so if sampling is compatible with periodization, you don't have to worry if you do it first, you sample first and then you periodize the samples, or you periodize the function and then you sample it, that's the same. And that's not always the case, but it's okay in this case. So I'm writing it, as SHA beta pointwise with SHA alpha convolved with f. So this is now a procedure that will help us to go into Cn. So it will help us to get from a given function first a discrete version, a time series, if we periodize, and then we sample. But now, how many samples of a periodic discrete signal do you need to describe it? And it's exactly n. And I can skip already the discussion of where should you put it. I mean, you should think this is element in L2 of the cyclic group of order n on the unit roots. So if I do the listing, the 0 will be at some place, it will be some component, and that should be glued on the torus at omega to the power 0. If I try to do this matching, then it's really the same to talk about discrete periodic signals, which are on the infinite thing, so kind of my tape now. in a discrete version, or I do it on the torus or on the unit circle. Next thing is, what is the Fourier transform now in the spirit of S0 prime? And then you will find out that this is, let's say, of the first part or so. I was telling you maybe that the Dirac comb, the sampling with beta is ST beta, so it must be D beta with SHA, and SHA goes to SHA hat. This will be not multiplied but convolved with F hat, and then this will be multiplied with the Fourier transform of the stretched ST row of ST alpha, so this here. Alpha of SHA, and that will be a sampling operator. So just looking up what you have here is, this is, of course, you can say it's 1 over alpha times stretching, which is this SHA alpha, multiplied with 1 over beta times SHA 1 over beta, convolved with F hat. So what we're seeing is, you start from a sampled periodized signal and you choose the order of wording, and you get to a sampled periodized version of its Fourier transform. That's already nice. So we can define it and we get in the right domain. Now the basic vector here is a vector x, and I told you it's in, I really like to write it as a group theoretical person, an element living on the discrete group of order n. And the discrete Fourier transform is telling me the FFT is generating an element which has the same length, which is living in L2 of the cyclic group of order n in the frequency space. Okay, now we have to discuss in 3 words, what is the frequency domain of the cyclic group? What are the mappings from the cyclic group into itself which are compatible with rotation, which means with multiplication? I give you a short list and then you see it's everything. You can take identity. It's a good mapping. It preserves multiplication into multiplication and everything is fine. I can identity square again. Set goes to set square. I can take the trivial character set to the power n. I can go set to the power n plus 3. And you will tell me, well, rotating a full circle is not counting. N plus 3 is the same as 3. So unit roots of order n, set n is away, and n plus 3 is the same as, so from 0 to n minus 1, taking powers is the dual group, and so you relabel it. So this is again L2 of set n. So as we can see it, we make vectors and vectors, and we have the idea that we can do cyclic shift on both sides, and that modulation in one case goes to translation, translation goes to modulation, multiplication goes to convolution, and so on. So on that group we have the easy theory. So essentially what we see is there is a factor that we have, and we have seen that there are now, by these things, some factors. And the interesting thing is, and I don't go through this, is this is the same as the description of this. So what you really have to do is to think, if somebody is giving you a discrete periodic sequence, it is repeating itself, and assume it's just a discrete sequence with period 4. So we have A1, A2, A3, A1, A2, A3, A1, A2, A3. Then the only thing what you have to know is, and really apply the rules, you have to know the SHA distribution, Dirac comp goes to Dirac comp. So I'm writing a periodic function which repeats 4 times as A1, a Dirac comp, which has the distance to the next A1. So with distance 4. And then it's A1, A1, A1. So I'm saying a periodic discrete signal is a Dirac comp, plus A1, a shifted Dirac, A2, a Dirac comp, plus A3, another Dirac comp, plus this. Then you will say, okay, then I know what the Fourier transform is. The Dirac comp at lattice constant 4 will go at Dirac comp at lattice constant 1 over 4. And if I do it A1 times, it's the amplitude. If I shift it, I have to multiply. What does it mean to multiply? I have to have phase factors. So the point is, that's why you have to do the bookkeeping carefully. These phase factors are, of course, exactly exponentials at certain positions where the Dirac comp on the Fourier transform is living. these are exactly the entries that you have in the definition of the DFT. So instead of talking about discrete periodic signals, and you are told you should look at them as function on the torus, and then you have the Fourier transform for the torus, you can also say they are really periodic functions, and you take the distributional Fourier transform, but it doesn't matter. Abstractly speaking, in the background there is the following simple story. If somebody tells you, I have isomorphic groups, then you have more or less everything living on this group is an isomorphism. When I was young, we still had the logarithmic books. So it was difficult to multiply large numbers if you don't have a pocket calculator or so. So how do you multiply large numbers? Well, people had obtained already tables with logarithms. So you give me two numbers, I would have to look up what is the logarithm of this. We were told we have to add the logarithm and then look up what the sum is meaning. Nowadays I'm saying, well, the positive real numbers with multiplications is a group which is locally compact abelian. The Haar measure is dt over t, and therefore you can take any isomorphism which is the exponential function which maps r plus into r minus, or if you start from the multiplicative side, you take the natural logarithm to go back, and everything you can do. So it's actually almost dangerous. I think now I can say, oh, now we can do Gabor analysis on the positive real axis. And somehow it's true. Yes, of course you can do it, but probably, I mean, normally I would, if I would have to review it, would say, well, the author has overlooked that it's the same. Maybe it's something very special that you can use, that maybe people use something and say, well, in a number theoretic problem, we're actually using Fourier analysis method on the line, but we use it now on the multiplicative group. It's then the Mellin transformer. So it looks differently, but it is not worthwhile to develop a Gabor analysis for the multiplicative setting, except you have concrete cases, or except you want to understand it. I mean, it's like the difference of driving in another country on the left-hand side as opposed to right-hand side. It widens your understanding of what driving means and progressing in one direction, and why the orientation of roundabouts is different, all these things. So, but that's kind of a little bit more of a joke. So we can think that practically speaking, if we have a nicely concentrated function, and which has some smoothness, then we should be able to recover the function more or less from these sampling values, and maybe we're able to recover the Fourier transform from these things. So the first question is, and I'm writing something like, what are we doing in MATLAB when we plot a function? And I zoom in and say, well, this would be the function, and we would plot kind of by hand by saying, well, we make an arithmetic progression, so maybe we do some linear spacing. I think it's linear space from A to B and 100 samples or so. So in the microscope, it would say, this is my position x1, x2, and starting with A and ending with B, we create this, and then we have the value, maybe the volume, the polynomial is evaluated, this is points, and then the command is plot at these points the values. And if you zoom in, what you would get, you would see these values. I try to make them equidistant or so, and you would see these values, and they are nicely connected, and clear enough. If you take enough points, it looks very much like the function. Now, my interpretation of what we are doing here, maybe in the middle term, is I'm doing, I'm not sure if I'd like to use another color. Yeah, I'm doing a summation over triangular functions. So you see already I'm using one of my favorite bupus. And I'm doing a spline approximation operator. Actually, I'm using here a spline interpolation operator. So it's the SP triangular system of f that I'm using. And you would say it's a sum over f of alpha n, and then a triangular function of width alpha, but again shifted to these positions. Sorry. Now it's better. So I'm shifting my triangular function to all these positions, and it's a triangular function like this. So that is my way of writing it. Triangular function compressed to the sampling lattice is adding up to 1 and no problem. But there's another way of writing it, and that's actually quite nice. It's d 1 over alpha of SHA convolved with st alpha of the standard triangular function. So first of all, I would like to bring it in a form where you can apply the rules that we have already. But what is the difference between this view and this view? Here I'm saying, well, I'm making the triangular function area 1, area preserving. The amplitudes blow up. Whereas here, the amplitudes are shrinking. So somehow you could say, these guys are uniformly bounded in the Fourier algebra sense. Yeah, maybe I should say, why is the left-hand side in S0 at all? Left the pen here, yeah. So this guy, individual guy, is in S0. Therefore, every shifted version is in S0 and it's the same norm. So how can I control the S0 norm of this? It's the sum of the samples of this multiplied with the norm of an individual triangular function in S0. So this is convergent because such a sum is not more than the Wiener algebra norm, and this in turn is less than the S0 norm. Remember, in the S0 norm we measure locally in the Fourier algebra norm. Riemann-Lebesgue tells us that's dominated by that's dominating the sup norm. So over intervals we control the sum of the maxima, and the sampling values are clearly this sum. Maybe there is some constant coming from the density of the sampling or so. But we can see, so these spline approximation operators, they are in S0. It's not just, I mean, they are clearly C0, continuous, decaying, and uniformly convergent. That's what we have proved. But I'm going for much more. And the normalization stuff helps a little bit because if I have amplitudes that are free, you can use that to have the effect that we have with the deltas. Remember, this is Riemannian sum. The width is in the denominator, or it's, no, you multiply with something which is getting small. So the factors that you have here additionally artificially increased are compensated by this factor. So this is really an identity. But now let us try to play what happens with alpha to 0. That's at the moment a completely formal argument. But you can, of course, imagine, sorry, something important is missing, and that's the f. Maybe I do my correction here. So I'm doing a multiplication with f. So the f is not changed. It doesn't go here. And then what I'm doing here is I have to see what the convolution operator is doing. The triangular function is the function with area 1. If you compress the triangular function, base is shrinking, it's a Dirac sequence. So this will go to delta 0. If you have now a lattice and you do it finer and finer, we're talking about Riemannian sums, integrating test functions at the end against, so it's constant 1. So we have constant 1. And that, of course, means that this is really, we can expect that this is going to f. So we have a completely formal argument, or at least a plausibility, that there is some chance this spline approximation operator, not for the rectangular function, which is used for engineering illustrations, but for the triangular function already, or for B-splines, then it's not interpolating but more smooth or so. It should converge to the f in this sense. Now I can tell you that we have a proof, so it's essentially, I've done it together with Norbert Keiblinger, that this is okay. So this is a whole paper, but the way to do it was more or less to look at the same story on the Fourier transform side. So we're saying, if I take a function and I sample it and then I multiply it, then I could also look at the same thing. I'm looking about a zero convergence. So I'm looking about something which I can take on the Fourier transform side, and I work with the same norm. So now, what is the analog of fine sampling? It's coarse periodization. So I have to think, well, somehow the Fourier transform is a nice function in the same space. Now I have the Fourier transform here. But first I have to periodize it. Well, we have tried to be careful. Our sampling is rather fine, so the periodization will be coarse. So there will be one copy here. There will be another copy here. But how can we get rid of these copies? These copies are making trouble, and we would like to cut out, but that's not what we can do here. The trick is, of course, we're cutting out in some reasonable way by smoothing. I mean, smoothing is filtering with a triangular function, is kind of removing the high frequencies. But, and again, all the time I use these operators and basic information, and that allows me to explain things without writing a lot of integrals. That's what you may have observed on this side. What is the Fourier transform of the triangular function? The triangular function is the sinc function. The Fourier transform is the sinc function squared. So the sinc function is starting at 1, going down like 1 over x. But now it's going down, it's positive. Another bump, going down like 1 over n squared. Not extremely well, but you can imagine that this is integrable, of course, and that's why actually the triangle function is in S0. It's compactly supported. The triangle has compact support, and the Fourier transform is sinc squared, and it's integrable. But now also this sinc square function will be stretched. The sinc function without stretching has its 0 at minus 1 plus 1, so it's interpolating. It's 0 at the origin and upon 1 at the origin and 0 at all the other integers. So we have now a sinc function. I have only 2 hands, so I can only move this. Maybe they are here. Now we start stretching it. We start stretching it. This goes to infinity, and I watch what this is doing. And observe, in the same way as I do the periodization, kind of here is my second copy sitting. So the whole situation is a situation where you're saying, I have the Fourier transform of this. If I periodize more and more coarse, kind of, yeah, I mean, I take any object, yeah? This might be the shape of the Fourier transform, of course, bump function or so. This is fixed. I don't change the I only change the center. Now I move the center. But there's a sinc function. I'm always at the integer position. So there's a sinc function, and it's 0 in the middle of this here. So of course, first you will say, well, if it's 0 here and this is on some big function or so, it's an interval of like this, it's fine. But if I go to further points more and more, the sinc function, because they are stretched, there's one function which is stretched, and they are fixed. So the amount where this function is supported will be always small relative to the values from a shifted sinc function near its 0. So it's very plausible already that the shifted sinc functions will kill all these copies. And the last and really thing where you have to be careful is, but how many copies do you have? You don't have to watch that each contribution is going to 0. That's already plausible, I hope, yeah? But that if you add up these things and these things and these things, that everything is working fine. So roughly speaking, the trick is again this epsilon over 7 trick. If I can prove it for a band-limited function, and then by approximation I can prove it for arbitrary function. So if everything is in the box, well, but because everything is dilated, I can more or less think the box is small. So I have to look at the maximal amplitudes of my dilated sinc function on a fixed interval. And the contributions add up like 1 over n squared, and that's good enough to control the overall effect. All these things put together are not really bad, and that gives you this convergence. So the resulting statement is, and that's maybe the last thing before we go to the break, is we can use, and there's a theorem done by Norbert Keiblinger a while ago, is if you take f and you take f alpha n, fine enough, and maybe you periodize, but if it's really almost compactly supported, it's good enough. Let's say Gauss function. I would not, if my FFT length is reasonable, I would not care about the periodization. But strictly speaking, we should periodize. Then you go to the samples. Then you apply the FFT. So it's a finite thing. Then you put it back to the positions, well, maybe gamma n. So at the right place. That's something I don't discuss. I mean, MATLAB will have an output which is FFT. We have to remember the first value is the guy sitting at position here, 0. The second one is probably at the second sampling point, and about 1/2 of them makes the right part, and the last one makes the left part. So we have to put them in the right, but we know what the SHA distributions are, what the dilation parameters are. So a musician would say, we have to relabel everything. It's not interesting to have the 27th Fourier coefficients is big. I would like to know is the energy at this 44 hertz loud or so. That's appropriately relabeled. But we put the values, and then we do, once we have finitely many values, we do pointwise linear interpolation or quasi-interpolation, gives a good S0 approximation. So somehow we have F, we have this as a Fourier transform, and we have a procedure that allows you to use the FFT and then go here, and we get a good approximation, and this will shrink as everything is getting better. So if we sample a nice function, S0 is not so high quality, a reasonable function that people would use as summability kernel for Fourier analysis or so, fine enough, long enough. Take an FFT and put it back to this continuous domain, then we have done a good job. And in the same paper by Norbert Keiblinger, he's also showing us, or that was one of the main purposes of really looking into this. If you have a Gabor atom, you're saying, I really want to see the Gabor, the continuous dual of a Gabor thing. So I'm interested in a Gabor situation. Then you can also say, well, what I have shown you in the session in the morning, that's the completely discrete model. But the Gauss function that we're using is exactly this periodized sampled Gauss function. That's actually why my Gauss function always has the name Gauss NK. It's Norbert Keiblinger. He said, well, that's the best way of doing it. And combined with the idea of now we do Gabor analysis and we compute it, and when we plot it, MATLAB is doing this interpolation for ourselves. We really have seen more or less the shape of these dual Gabor atoms in the continuous setting due to the result that he has. So this is one of the situations where we can say that the continuous is approximated. And what I also like is when you want to compare the quality. So somehow this is in a way, make two more minutes. If I say that this is an approximation to the limit, and if I'm in a situation where I do not know whether I'm approximating the limit, then you would say, well, then verify the Cauchy condition. So I can play the game and say, well, I do it for some n and for more n or so, but how can I compare an FFT with value lengths, I don't know, 300, another with 400? I think it's a good idea to compare two such things where the factor is 4. Because again, if I take my 12 and 1 over 12, then my idea was, okay, you're saying periodizing with length 12. So where would you start to sample? You would start to sample the Gauss function from -6 to +6. You get 12 unit intervals, each of them delivering 12 values, so we have an FFT of length 144. It's harmless and nice. Now I'm saying I want to improve the quality. What would you improve? You would improve the length of the period would be twice as long, so make it 24. So I'm sampling from -12 to +12. I'm sampling at the rate of 124 because then it's good compatible with the FFT. Now it's 4 times as many values. But the 4 values, let's say first we had 144 and then we have 4 times as many values. But how are they intertwined? And then you have to think, we always start with 0, and 0 is in all these sampling sets. So the first coordinate should be the same value if I do an approximation. The second one is because of my fine sampling. The third one is actually the position of an old one. And then we go until we go from 0 to geographic location 6. And then we get a lot of values which are, actually a lot of them, sampled at 1 over 24 from 6 to 12. They are not interesting. Then we go from the other side, we take these samples, they're also not interesting. But from the last segment, we take again every second. And there I would say probably should go until the 4n minus 1 component, moment minus 2 component, because the very last should be probably, since the first component in our vector is a 0 component, in the fine sampling, the last component must be from the fine family. So only the second last is from the old family. So I would compare the values reading the fine FFT from actual length -1 down, stepwise 2, until I'm at -6. And that's a quite general thing where I think we will have to do some more research. So to say, if you're thinking that you're approximating the continuous situation in a time frequency spirit or on time side and on Fourier transform side, go from n to 4n. If the piecewise linear interpolation of my coarse approximation using FFT of length n and the actual FFT of length 4n are very, very similar, then I think one should be able to justify it by some abstract arguments. Okay, sorry for going so much overtime, but I was starting a little bit later. Thank you, and we take a break.